I want you to imagine you're studying for the most difficult exam of your life. The exam covers 10,000 textbooks. To answer one single practice question, you have two possible strategies. The first one is a strategy A, or the perfectionist. You read all 10,000 books, you verify every fact, you cross-reference every footnote, you check the index, and only then, after reading 5 million pages, you write down your answer. You will be 100% mathematically correct, but it will take you 20 years to answer that one question. You will be 80 years old before you finish the test. The next strategy is the cheater. You grab one random book off the shelf, you read one page, you make a wild, gut check guess based on that one page. You check the answer key, you adjust your mental model, you move to the next question. This strategy is messy, it's chaotic, and it feels wrong. Strategy A is what we call batch gradient descent. It is the mathematically correct way to do calculus. Strategy B is what we call stochastic gradient descent, or SGD. It is the noisy way. But here's the secret every senior AI engineer knows. In the world of deep learning, being perfect is enemy. If you try to train a neural network by looking at your data at once, you will run out of memory, you will run out of time, and ironically, your model will probably be worse. Today, we are going to learn about the mechanics of training. We are going to explore SGD, mini batches, and the hidden hardware secrets of your GPU. We'll answer the questions that plague every junior engineer. Why is my loss curve jumping up and down like a heartbeat? What exactly is the difference between an epoch and an iteration? How do I train a massive LLM like Llama 3 when I only have 24 GB of VRAM? By the end of this video, you will understand why noise isn't a bug, it's the most powerful feature in the deep learning. Hey everyone, welcome back to Sumantra Codes. I'm Sumantra. In our previous video, we established two pillars of AI. First, the map, or the loss function, or JW, that tells us where we are. Second is the hiker, or the gradient descent, which tells us how to move downhill. The update rule for the hiker is simple. W new is equal to W old minus alpha dot nabla j of weights. We update our gradients by moving in the opposite direction of the gradient, or nabla j. But there is a hidden dangerous variable in this equation that textbooks often gloss over: the gradient itself. How do we actually calculate nabla j? Mathematically, the true gradient is the average slope of the error for every single data point in your entire universe. Let's look at the math. If you are training a standard ResNet 50 on ImageNet, you will have 1.2 million images. To take one single step down the mountain, just one update, you have to first feed image 1 into the network, calculate error and backpropagate, then feed image 2, calculate error and backpropagate. Similarly, we'll go until we'll feed 1.2 millionth image, calculate error and backpropagate. Sum up all those gradients, divide by 1.2 million to get the average. Update the weight once. This is called batch gradient descent or vanilla gradient descent. It is precise, it moves directly downhill, it follows the curvature of the earth perfectly. But let's talk about the cost. If processing one image takes 0.01 seconds, processing 1.2 million images take 12,000 seconds. That is 3.3 hours for one single step. To train a model, we usually need 100,000 steps. Do the math. That's 37 years. You cannot train a modern AI this way. So we need a compromise. We need to slide along a spectrum called batch size. We need to trade perfect accuracy for speed. Let's visualize this with an analogy. We have three hikers trying to navigate this foggy mountain range to find the valley. First is the hiker 1, or the perfectionist. He uses method batch gradient descent. His batch size is n, or entire data set. His behavior: he stops at every single step. He pulls out a surveyor tripod, a laser rangefinder, and a topographic map. He measures the slope of the entire mountain range for 3 hours. Then he takes one confident, mathematically perfect step. Pros: the path is smooth, it never fluctuates, it guaranteed to converge to a local minimum or for convex problems. The cons: it takes eternity. Also, it requires massive memory to store gradients for 1 million images before averaging. Next, we have hiker 2, which we call the trunk hiker. He uses the method Stochastic Gradient Descent, or SGD. His batch size is 1. His behavior: he picks up one random rock, or one image. If that image implies go left, he goes left immediately. If the next image implies go right, he goes right immediately. The reality, individual data points are noisy. Maybe image 1 is a weird blurry picture of a cat that looks like a dog. It tells the model to move in the wrong direction. The hiker stumbles. It's pros, it's blazing fast. You update weights millions of times per epoch. The cons are it's chaotic. You might never settle at the absolute bottom. You just vibrate around it, buzzing like a bee. And finally, we have a hiker 3, which we call the pragmatist hiker. The method he uses is mini batch gradient descent. His batch size is B, usually set of 32, 64, 128 or 256. His behavior, he grabs a handful of rocks, he averages their advice. The weird blurry cat is cancelled out by 31 normal cats. The advice is mostly correct. The noise is dampened. This is the sweet spot. It is stable enough to converge, but fast enough to train on a GPU. There is a massive hardware reason why mini batch is the standard. GPUs or graphics processing unit are SIMD machines. Single instruction, multiple data. This means a GPU can multiply one number just as fast as it can multiply 32 numbers, provided they are in vector. If you feed GPU one image or SGD, you are using 1% of its scores. The other 99% are sitting idle, burning electricity. If you feed it 32 images on mini batch, you use 32% of its scores in the same amount of time. You get 32 times the throughput for free. So the key takeaway is always use mini batches. SGD or batch size 1 is too slow on hardware. Batch size n is too slow on math. Mini batch is the Goldilocks zone. Now here is the counterintuitive part. This is what separates the junior from the seniors. You might think, Sumantra, if I had an infinite computer with infinite RAM, I would always use batch gradient descent, right? Because it's perfect. No, you would actually still use mini batches. Why? Because noise is good. So let's imagine we have two valleys. The first is valley A, which has a sharp minimum. It is deep but very narrow, like a needle. The next valley is valley B, which is a flat minimum valley. It is slightly less deep but very wide, like a soup bowl. If we use the perfectionist hiker or batch gradient descent, he will find the deepest point mathematically. He might fall into valley A, the sharp minimum. He stops. Training loss is 0. Perfect score. But what happens when we ship this model to production? In the real world, data is slightly different. The landscape shifts slightly. If the landscape shifts just 1 millimeter to the left, valley A moves. The model is now standing on a cliff. The error skyrockets. Sharp minima is equal to a bad generalization. Now imagine our pragmatic hiker or mini batch standard gradient descent. He tries to enter valley A, but because he is noisy, because he is stumbling around based on random batches, he can't stay in the needle. He keeps bumping into walls and jumping out. He literally cannot settle in the sharp minimum. The noise kicks him out. Eventually, he stumbles into valley B, the flat minimum. He bounces around, but because the valley is wide, he stays inside it. When we ship valley B to the production, the data shifts. The model is still inside the bowl. The error remains slow. Flat minima is equal to a good generalization. There is a major theory in deep learning, the flat minima hypothesis. The noise of SGD acts as a form of regularization. It prevents the model from memorizing specific brittle pattern. It forces the model to find robust, stable solution. So we don't just tolerate the noise, we rely on it. Before we go further, we need to fix a vocabulary problem. I see senior engineers mix these up in the meetings. Let's clarify them once for all. So I have a scenario where the data set of size n is of 1000 images and our batch size B is of 100 images. So let's define the first term, iteration or step. An iteration is one update of the weights. It corresponds to passing one batch through the network. In our example, we pull 100 images. We compute loss, we update weights. That is one iteration. The second term is epoch. An epoch is when the model has seen every single image in the data set exactly once. In our example, we have 1000 images. We take 100 at a time. We need to do this 10 times to see all 1000 images. So 1 epoch is equal to 10 iteration. So iteration per epoch is equal to total data set size divided by batch size. So if you're looking at your training loop progress bar like TQDM and it says epoch 5 out of 50, step 450 out of 900, it means we are passing on the 5th pass through the entire universe of data. Inside this pass, we are halfway through the batches. Then we have a rhetorical question. Why do we need multiple epochs? Why isn't one pass enough? Think about learning a song. Can you memorize Bohemian Rhapsody by listening to it once? No. You need to listen to it multiple times. Similarly, the neural network needs to see the data multiple times to adjust the weight incrementally. We usually train 10, 50, or even 100 epochs. Finally, a pro tip for the modern era of LLMs. We established the batch size. We established that batch size matters. In LLM pre-training like GPT-4 or Llama, scientists discover that massive batch size like 4 million tokens or batch size like 4096 stabilize training significantly. A batch size of 496 high-resolution images simply will not fit into your GPU memory or VRAM. If you try to load 4096 images into a standard NVIDIA A100 with 80 GB memory, it will explode. You will get dreaded CUDA out of memory error. You can maybe fit 32 images. So we are stuck. Do we have to use small batches? No. We cheat the system using gradient accumulation. Here's the algorithm. We want to simulate batch size of 128, but we can only fit 32. So our first step is to load mini batch of 32. Run forward pass, run backward pass. The crucial thing is do not update the weights yet. Do not call optimizer.step in PyTorch. Just take the gradients and pour them into the bucket. The second step is to load the next mini batch of 32, run forward and backward passes, add these new gradients to the existing gradient in the bucket, and then repeat this 4 times. Now, the bucket contains the sum of the gradients from 32 into 4, which is equal to 128 images. Now, we call optimizer.step. We update the weights and we empty the bucket by calling optimizer.zeroGrad PyTorch function. Mathematically, this is identical to training with a batch size of 128. Physically, you never held more than 32 images in memory at once. The trade-off, you traded time for memory. It takes 4 times longer to do one update, but you didn't crash your GPU. This is the standard way to fine-tune models like Llama 3 or Mistral on consumer hardware. Now let's recap the mechanics of training. We have the spectrum. First is the batch gradient descent, which is accurate, theoretically perfect, but computationally impossible. Next, we have stochastic gradient descent or SGD, which is fast, chaotic, but inefficient on GPUs. And finally, we have mini batch gradient descent. The standard, it balances speed via GPU SIMD vectorization and stability. Next, noise is a feature. The pragmatic walk of mini batch descent help the model escape sharp minima or bad generalization and find flat minima or good generalization. And then we have vocabulary. We define iteration as one update step. We define epoch as one full pass through the data. The next is gradient accumulation, a vital trick to simulate massive batch size on limited hardware by summing gradient over time. The next time you type batch underscore size is equal to 32 in your Jupyter notebook, realize what you're doing. You aren't just saving memory, you're hiring a pragmatic hiker. You're telling your AI, I don't need you to be perfect at every step. I need you to be fast. I need you to explore. And I need you to find solution that actually works in the real world. I have one question for you. What is the standard batch size you use? Are you a member of batch size like 32 Club? Or do you have a hardware to push it to the batch size of 1024? Let me know in the comments below. If you learned something new today, especially about flat minima or gradient accumulation, hit the like button. It creates stronger gradient signal for the YouTube algorithm to recommend this content. And make sure to subscribe to Sumantra Code. Thanks for watching and keep iterating.